Hello, Math 2000, Linear Algebra. It's Professor Wenson here with a video on Section 1.1, Systems of Linear Equations. So starting here, this is your Canvas page. Now I'm in the teacher view, but you'll see the same exact modules. And every week a new module will open up with sections I recommend you study and read and do work on. Even though almost everything, the assignments and ZyBooks activities aren't due until Sunday, May 9th. I just recommend you do these this week, and I'll have recommendations each week so that if you keep up with those, you won't be overwhelmed at the end of the semester. So there's a page for section 1.1, and every single page is going to look pretty similar. I'll ask you to read section 1.1, Systems of Linear Equations, in your ZyBooks text. So you're going to have to go to a separate website. Just go to zybooks.com and sign in. Hopefully you've purchased access to ZyBooks by the time you're watching this. Get a password and all that, and be able to sign in, and then subscribe to my Math 2000 book. So read section 1.1 in the ZyBooks text, and while you're reading it, you'll come across the participation activities in orange and challenge activities in blue sometimes. Do those as you read. And as I mentioned earlier, everything's due by 11:59 p.m. on Sunday, May 9th, but I would recommend you do this this week, week 1. And if you're struggling, if things in the ZyBooks aren't making that much sense to you, you can come back here to this page and watch some videos related to the topics. I just have a couple here related to the topics in section 1.1, but also this video that you're currently watching. So in this video, I'm going to be going over section 1.1. And hey, it looks like some of you have already started, and you should be able to see also what percentage of the challenge. If you open up a chapter, you can see what percentage of the challenge activities and participation activities you've done in every section. And after this week, after week 1, so the beginning of week 2. I will enter scores in Canvas for your challenge activities and participation activities for section 1.1, 1.2, and 1.3. Those won't be your final scores, right? I'll just enter what you have right now after week 1, and later on, if you finish it, I'll change the score as well. So if I enter a 0 for you in section 1.3, for instance, on Monday in week 2, that won't stay a 0. Okay. Alright, so let's go into section 1.1, Systems of Linear Equations. Alright, so I'm not going to read everything word for word to you. I'll just highlight the important stuff, and I'll go over some of the participation activities, just not all of them, and some of the challenge activities as well. Again, I'm not going to do everything for you. I'll just start you off in a lot of the participation and challenge activities. So you have a paragraph here. Now every section will open up with some objectives, right? You'll be able to identify a linear equation, determine whether an n-tuple, right? You'll learn what that is a solution to a system of linear equations, identify the type of linear system geometrically, and set up a system of linear equations that models a real-life situation. So word problems. Alright, so what are linear equations? A linear equation is an equation of the following form. So any equation that can be written this way, they don't start off all looking like this, but any equation that can be written this way is a linear equation. a1 times x1 plus a2 times x2 plus, a3 times x3 and so on, plus all the way up to an times xn equals b, where all these a1, a2, a3, all the way up to an, the ai's are called the coefficients. They're real numbers. x1, x2, x3, x4, all the x's are the variables. And b is some other real number. B is a constant, has no variable attached. Alright, so every single term is a number times a variable to the first power, plus a number times a variable to the first power, and so on, equals some number on the other side. To graph, right? You've seen graphs in algebra class. Remember, a graph is just a picture of solutions to an equation. A graph of a linear equation with two variables is going to be a straight line on the two-dimensional plane. A graph of an equation with a linear equation with three variables is going to be a plane, right, like a sheet. That's not all of it, right? A plane goes off forever in two directions, and this isn't the whole plane right here. But the graph of a linear equation in three variables is a plane in three-dimensional space. And graphing, linear equations in 4 dimensions, 5 dimensions is not possible, right? You can't really picture that because we only live in a three-dimensional world. All right, so here's a orange, right? Participation activity. Now I think this is already completed because during my week 0 video on on the syllabus I went through this, so that's why it's already complete for me. The first time you see it, it's going to be an empty box up here without a check mark. That means it's not complete. You have to answer all the questions. Alright, determine if each equation is a linear equation. So 5 times x1 plus x2 minus 7 times x3 equals 4. This is of that form where every single term is a number times a variable to the first power, plus a number times a variable, 1x to the x2 minus 7x3 to the first equals some constant 4. This is a linear equation. It does take on that form, right? And it explains why you're correct over here. Like I said, I'm only going to start you off. There's 6 of these, so I'll do half of them. Right? The square root of 5 times x1 plus 4.6 times x2 plus half times x3 equals negative 5. This is a number, square root of 5 times x1 to the first, plus a number times x2 to the first, plus a number times x3 to the first equals a number. This is a linear equation. I know there's a fancy square root there, but the variable is not in the square root. The number is, right? The square root of a number is just another number. Now this doesn't take on, all the variables aren't on the same side, but every single term that has a variable is just a number times a variable to the first power. So this is also linear. Alright, maybe I'll do some just for this first one, because we haven't seen any ones that aren't linear yet. These two are not linear. The reason being is, look at the term with the variables. It's a number times a variable to the first, but then times another variable, right? So it doesn't take on this form where each term in a linear equation is just a number times a variable to the first power, or just a number itself. So that's not linear because of the x1 times x2 term. See, this is not linear because of x1 cubed. It's not to the first power. All right, so let's say 6 is linear. Might as well throw it in there. Okay. Now, a system of linear equations, or a linear system, is a collection of one or more linear equations involving the same variables. So a system of m equations in n variables has the following form. So you see that m equations, and each equation has the same n variables, x1 to xn. All right, so an example, here's a two equation system with two variables. x1 plus x2 equals 2, x1 minus x2 equals 4. All right, a solution of a system of linear equations with n variables is an ordered list of n elements or n numbers called an n-tuple. Now, if there's only two variables, this is usually just called an ordered pair. You've probably heard that term before. If there are three variables in the system, usually it's called an ordered triple. But if there are more than three variables, then you'll see 4-tuple, 5-tuple, 6-tuple for lists of 4 numbers, 5 numbers, and 6 numbers respectively. Written like parentheses, and then a value for the first variable, a value for the second variable, all the way up to a value for the nth variable. And it's one of these that satisfies every, right, this is the key word here, right? Every equation in the system, not just one of them or two of them, but all of them, right? If there's 5 equations, all 5 equations have to be satisfied in order for an n-tuple to be considered a solution. To determine whether an n-tuple is a solution to a system, each element is substituted into the corresponding variable. If the result is true for all equations, then the n-tuple is a solution. Alright, so this one here, I'll go to some paper, pencil and paper, pen and paper demonstrations for you at times. This first section is not too deep, so I'm not going to do too many pencil paper stuff, but on occasion when I'm doing these videos for you, I'll switch over to some pen and paper. Alright, so here's another example of a participation activity. Again, I completed this activity for you, with you, in the week 0 syllabus video, so that's why it's already filled in. This is one of those animations where you hit start, and it says to determine whether the ordered two-tuple or ordered pair 3, -1 is a solution to this system x1 plus x2 equals 2, x1 minus x2 equals 4. The first value, 3, is substituted for x1. The second value, -1, is substituted for x2, and they've done this here. So I take the first equation, right, x1 plus x2 equals 2, replace x1 with 3, replace x2 with -1, 3 plus -1 equals 2, that's 2 equals 2, that's true. Do the same thing, x1 for the second equation, x1 minus x2 equals 4, replace x1 with 3, x2 with -1, that's 3 minus -1, or 3 plus 1 equals 4, that's true as well, 4 equals 4. Alright, play the next thing, Since the resulting equations are true, right, both of them, all the equations are true, this ordered pair, this two-tuple, 3, -1, is a solution to the system. The ordered pair 2, 0, or the ordered two-tuple 2, 0 is not a solution to the system, because substituting 2 for x1 and 0 for x2 in the second equation fails to yield a true statement, right? You see that if I replace x1 with 2 and x2 with 0, the first equation is true, great, but the second equation is not. You get 2 equals 4. So that the ordered pair, this ordered two-tuple, is not a solution of the system. It's a solution of one of the equations, but not the whole system. I hope that makes sense. This is probably looking familiar to you from intermediate algebra or whatever college algebra class you've taken before. And you see, now I'm done with the animation and stuff, and it would say I was complete. And then again, I showed this in the week 0 syllabus video. Alright, now see, this is what you should normally be seeing, right? A participation activity. All these activities should start out blank. Alright, so there are 6 of these. I'll just go for the first 2 or 3. Now, bear with me here. Like I said, I'll work on pencil and paper. This first video will take a little longer. I'll do some more explaining than I will in future videos. But this one I'm just going to kind of out loud. Right? So determine if the given n tuple is a solution to the system. So is the ordered pair 1, 3 a solution to 2x1 plus x2 equals 5 and x1 minus x2 equals negative 5, right? So this tells me, to check, I replace x1s with 1 and the x2s with 3. All right, let's see. Is 2 times 1 plus 3 equal to 5? Yes, it is. That's true. 2 plus 3 equals 5. Is 1 minus 3 equal to negative 5? No, it's not. That'd be negative 2 equals negative 5. So this ordered pair is not a solution. And again, the explanation over here. And you see that question's complete. Put a little check mark. I'll just do one more. Number 4. This is an ordered triple or an ordered 3 tuple. And here I have a system with 3 variables. When I replace x1 with 5, x2 with 1, all the x2s with 1, and all the x3s with negative 1 are all 3 equations true statements. So is 5 plus 1 minus negative 1, so that'd be also plus 1. Is 5 plus 1 plus 1 7? Yes. First equation's true. 4 times 5 is 20. Plus 1 is 21. Then plus 3, right? Negative 3 times negative 1 would be plus 3. So 20 plus 1 is 21. Plus 3 would be 24. You get 24 equals negative 2. That's not true. So I don't need to check the third equation. I know it's not a solution. All right. Sure, it satisfies the first one. It also satisfies the third equation. It doesn't satisfy the second equation. So it's not a solution. And you can do the others, I hope. All right. Oh, here's one with an ordered 4 tuple or an ordered quadruple. I replace all the x1s with 1, all the x2s with negative 4, x3s with 8, x4s with negative 2. And it works that way for no matter how big the thing is. Right? All right, now I'm getting to a challenge activity, which are in blue. And again, they're like the participation activities, only a little more challenging. You have to do a little more thinking and usually more entering answers. So I hit start, all right, and there are, down here it tells you there are 3 levels, 3 questions to complete to fully, and you see the 3 here. And once all 3 are complete, you'll see that this box in the upper right-hand corner will fill in blue with a check mark. Say I determine whether, again, I'm just going to do these are just determining whether one ordered pair is satisfying a system. So I'm just going to kind of do this out loud, not on pencil and paper, not with pen and paper. So does 0, 1 satisfy these equations? So it has a question over here, does it satisfy? Yes or no? Check the ones that it does. So when x1 is 0 and x2 is 1. So 3 times 0 is 0, plus 1 is 1. Not 2. So no, I'm not going to check that box. So I can answer this question right now. Is 0, 1 a solution of the system? No, it's not. I'll put that in. All right, how about the second equation? 2 times 0 is 0, plus 1 is 1. Neither equation is satisfied, so I'm going to fill in neither of these boxes. Say, this is not a solution of the system, and then check my answer. And it'll come back green, or if you're wrong, it'll be like a red X and have you do another one. All right. So let's do one more of these. So I hit next, and it'll take you to the next level. And you can go back to the level 1 again if you want for some reason. All right. So here is this ordered triple satisfying, again, does it satisfy each equation? And then the final thing, is the ordered triple a solution of the system? So is 3 times 1, that's 3. 2 times negative 1 is negative 2. 3 plus negative 2 is 1. Plus negative 2 is negative 1. So it doesn't satisfy the first equation. It's not a solution. But I got to check the other two. One of these might be satisfied. So 3 minus 3 is 0. Plus negative 2 is negative 2. That's not satisfied. 2 plus negative 2 is 0, plus negative 2 is negative 2. None of them are satisfied again. And it's definitely not a solution if none of them are satisfied. Anyway, it's got to satisfy all of them. All right, and then I hit next and go to the third one. I'm not going to do the third one, but you see what's going on here, I hope. All right, and then you have an ordered 4 tuple, and you plug 2 in for x1, 1 in for x2, 0 in for x3, -2 in for x4, and see if each of these are satisfied, and then answer the question: does this ordered 4 tuple satisfy a solution, the system of equations? All right. The next part: the geometric representation of a solution to a system of linear equations. Okay, so pictures, right, in 2 dimensions or 3 dimensions. So a system can have one solution. A system of linear equations, right, can have exactly one solution, no solution, or infinitely many solutions. Okay, there may be infinitely many n tuples that make all equations true, or just one of them, or none, or nothing. So without exception, one of these 3 scenarios applies to a given system. No other possibilities exist. All right. Now here are some terms that you're going to need to know. A consistent system has one solution or infinitely many solutions. So a consistent system just has solutions. It has ordered pairs or ordered triples that make all the equations true. And the opposite of that, an inconsistent system has no solution whatsoever. No matter what you plug in, you're not going to get all the equations to be satisfied. All right. So a 2-dimensional system of equations has 2 variables, and equations I mentioned earlier, linear equations with 2 variables, their graphs are straight lines. And 3-dimensional systems of equations have 3 variables, and remember I said earlier in the section, the graph of linear equations with 3 variables are planes in 3-dimensional space. And the solutions of systems will occur where there are intersections, right? Notice the word intersection popping up here a couple times. Intersection of lines, intersection of planes. Right? So here, see, here's some examples of systems with 2 variables, right? 2 equations, see how there's 2 lines here. 2 equations, 2 variables. And what you're looking for when you're looking for the solution of a system is the point or points where all the lines intersect, or all the graphs intersect. All right, so I'll start this and just flow through this. So a consistent system, right, may have only one solution. In the case of a system with 2 variables and 2 equations, the point where the 2 lines intersect is the only solution. So like here, if this was the graph of my system, the point 0, 1, right, that ordered pair would be the only solution of the system, right, the only pair that satisfies both equations. But a consistent system may also have infinitely many solutions. Did you see the 2 lines come together there? The lines coincide, which means that every ordered pair on the line is a solution to both equations. So this is one line right on top of the other. So every single ordered pair on this line satisfies both equations in the 2-variable system and would be considered a solution. Now the third scenario with 2 variables and 2 equations is if you have 2 parallel lines, 2 lines that don't cross. Like that red line, that blue line there. They don't intersect, so this would represent or be the graph of an inconsistent system, right? Something without a solution. All right. Now in the participation activity, we go into 3 dimensions. All right, determine the type of each linear system in 3 dimensions. So when when we have suppose you have 3 equations with 3 variables each, 3 linear equations with 3 variables. The graphs of those equations would be planes, right? Sheets in 3-dimensional space. And what you're going to be looking for is are there any points where all of the sheets, all of the planes intersect? So in this first scenario, right, you have the blue, the pink, and the gray plane. Right? You see how they all have this one, this is like the corner of a room here. These are like walls. They all have this point in common. So there is the one solution, one point that's on all three of these planes. So this is a consistent with one solution system. Here I have three planes drawn that are all parallel. They never touch. So this is representing an inconsistent system. All right, now here's where it gets tricky. Remember I said, we're looking for points that all the planes have. Sure, the blue plane and pink plane have these points in common on this little line. The gray plane and the pink plane have this line in common. The blue plane and the gray plane have this line in common. So like if you take any two planes, they intersect. But the question is, do all the planes intersect each other at some common point, and that, or common points, and that's not happening here. There is no point that is on all three at the same time. So this is also representing an inconsistent system. Now, again, tricky with 3 dimensions, but this is the same thing. Yeah, the blue and the gray intersect. Sure, the blue and the pink intersect. But do all three of them intersect with one another? Are there any points that are on all three? So again, this is inconsistent. And then here, all three have a line in common. This black line, these points are on all three planes, right? But a line has infinitely many points, so there are infinitely many points on all three planes, meaning the system is consistent with infinitely many solutions. And this is kind of implying that all three planes are the same plane, kind of like how when both lines were the same line earlier, they just drew them right on top of each other, like this here. Right? When all three, this is just implying that all three planes are the same plane. They're drawn right on top of each other. They're all intersecting each other at all places. So another consistent with infinitely many solutions. So again, I'm not going to do this with every section where I go through all the participation activities. I'm just doing this for this first section, right, just to get you used to ZyBooks. All right, now we're getting into some applications of linear systems. This is word problems. All right. So follow these steps, and you've seen this in a college algebra course or whatever algebra course you've taken prior to this. You identify the given quantities, identify the unknowns. What do they want? What's being asked for. Assign variables to the unknown quantities. And then, read back through the problem and set up equations based on known geometric formulas or physical laws. Like, distance equals rate times time, or interest, the interest accrued is equal to the principal amount times the interest rate times the time in the account, and stuff like that. That's stuff we're going to be using here in this section. All right, so another animation. All right, you've seen the animations. You start, you play, you read, follow along. I'm going to leave that to you. Okay, so this one I'll actually go to the pen and paper for. All right, I'm not going to write down the problem. I'll just keep transferring back and forth between these two, so bear with me here. But we have a camper rows a boat downstream to a picnic shelter. All right, a total of 7 at a total speed of 7 miles per hour. All right. On the return trip, the total speed of the boat is 1 mile per hour. Set up a system of equations to find the boat's speed in still water, right? So just if the water weren't moving, and the speed of the current. Right. So again, like I said earlier, you've probably seen stuff like this before. So I'm drawing a little picture here. So here's this river. All right, and they're saying this camper rows downstream. All right, now downstream means with the current. All right, so let's say the river is flowing this way. I'll put a little arrow. All right. and the camper is rowing downstream, so getting, so you got the speed of the boat with the current. Right, this would be with current downstream, and ends up at this campsite. Ends up at this campsite that's 7 miles, and the total speed is 7 miles per hour. All right, and then on the return trip, the camper is rowing up the current. This is again upriver against the current. All right, so that means that the water is slowing the boat down, and is going slower at only 1 mile per hour. And it says set up a system of equations to find the boat's speed in still water. All right, so I identify what they want from me, right? What are the quantities, right? The boat's speed in still water. I'll just label, and then that's I'll call that B, right? And I'll just call it the variable B. Or to be consistent with other problems in the section, how about x1? Because we've been seeing a lot of x1s and x2s. And the speed of the current. The speed of the current, right? The speed of the water. Again, I can call that C for current or x2. Right? I'll use these two just to stay consistent with the actual the section. All right, so with the current, they said the total speed, right? Total speed was 7 miles per hour. Now, the total speed is the speed of the boat on its own, right? In still water. You're going with the current, so you're adding to it the speed of the water. So this is x1 plus x2, the speed of the boat in still water plus the speed of the current should be equal to 7 miles per hour. So I'm getting an equation here with two variables, x1 plus x2 equals 7. I hope that made sense, right? That's with the current. Then going back, right, against the current, your total speed is 1 mile an hour, it says, total speed. And total, adding. So the speed of the boat, x1, plus, now this time the water is slowing you down. So you're adding the opposite, you're subtracting the speed of the current this time. So with the current plus x2, against the current minus x2. And that total speed on the trip back was 1 mile per hour. So here is my my system of equations related to this particular problem. And then we'd be asked to solve this system. All right. Now, in the participation activity, right, you're not asked to solve it. You're just asked to set up the system. And so you see down here the very last part, what's the system associated, and I just got it here, right? x1 plus x2 equals 7, x1 minus x2 equals 1, and hopefully that made sense with the current against the current. All right. Yeah. And again, we're not solving anything yet. I know you know how to solve some of these from a previous algebra class. We're going to get into procedures for solving systems, linear systems, later. All right, so here's another example, solving a mixture problem. Okay, again, I'm going to leave that for you to read and do my own, and just do the participation activity, and that looks like it'll be it. All right, so we have formulating a meal plan. A dietitian formulates a meal plan for a client who needs 58 grams of protein, 60 grams of carbohydrates, and 3 grams of potassium. The nutritional facts for a meal served by the cafeteria is given in the table below. All right. So beef brisket has 9 grams of protein, no carbs, no potassium. Mashed potatoes has 2 grams of protein, 11 carbs, and no potassium. And fruit salad has no grams of protein, 10 grams of carbs, 1 gram potassium. Okay. Set up linear equations to determine how much how many servings of each meal the client needs to satisfy the given dietary requirements. All right. So what should be assigned? All right. Well, the question is how many servings of each meal. All right. So the amount of servings of each of the meals. So the amount of beef brisket, the amount of the number of servings of mashed potatoes, and the number of servings of fruit salad. That's what we're being asked for. So I'm going to go write this down. Again, for this, I would say I'd let x1, and you could call it some other variable if you want, like beef or beef brisket. But just to stick with what they have here, just to be consistent with the section, I'll say x1 be the number of servings of beef brisket, and x2 be the number of servings of mashed potatoes, and x3 be the number of servings of fruit salad. Okay, so I'd start off with that, identifying what they want from me, my unknowns, and assigning them variables, x1, x2, x3, and then setting up equations from this. The total number of the total number, the grams of protein they're requiring me to get, this person, the client, to get 58 grams of protein. So each serving of beef brisket will give me 9 grams, of protein. Each serving of mashed potatoes will give me 2 grams, and each serving of fruit salad will give me no grams of protein. So if I make an equation for the protein, again, every serving of beef brisket's giving me 9 grams, so there are 9 times x1 grams of protein when I eat, x1 servings of beef brisket. And then I would add to that the number of grams of protein from the mashed potatoes, and it said there were 2 grams of protein in every serving of mashed potatoes, so 2 times x2. And then add to that the number of grams of protein from fruit salad, but it said there were no grams of protein from fruit salad. And the dietitian wanted this total number of grams of protein for the person to be 58 grams. So grams of protein from beef brisket plus the grams of protein from mashed potatoes needs to be 58. All right, then I'll do the same thing for carbohydrates and potassium, 60 grams of carbohydrates. So, every serving of beef brisket has no carbohydrates. Every serving of mashed potatoes has 11 grams of carbs and 10 grams of carbs in fruit salad. So no x1 plus 11x2 plus 10x3 equals 60, right? The dietitian wants 60 grams of carbs. So again, no x1, 11x2, and usually you'll see people often write things so that the terms with the same variables are lined up. Plus 10x3, right? There were 10 grams of carbs in every serving of fruit salad, so 10 times x3 grams of carbs in the fruit salad. It needs to be equal to 60, right? 60 grams of carbs. And then finally, for the grams of potassium, recommend 3 grams of potassium. The only thing providing potassium here is the fruit salad. And there's only 1 gram of potassium in every serving of fruit salad. So x3 needs to be equal to 3. Right, that's my third equation. And x3 needs to be equal to 3. And then again, I'm not solving the system. Right? Here's a system of 3 equations in which 3 variables appear, x1, x2, x3. I've labeled what the variables represent. This is the carbs equation, right? This one here, and this is the potassium equation, POT, right? POT. And we're not going to be solving it yet. I know you already probably know how to solve these. You've seen it in a previous algebra class, but all we're doing here is are you able to set up the system, all right? And they ask for what is the equation for carbs, what is the equation for protein, for potassium. I already wrote all those out. All right, and then you have additional exercises. Now I'm not going to do these. All right, back in your Canvas page, you will see in each week an assignment. So here's assignment 1 on the sections I recommended from this first week. And when you open that page, you'll see these problems that I'm asking you to do are all taken from the additional exercises. All right. And I'll show you what this looks like as a student. Right. Oh, yeah, I forgot. I'm recording this before I unlocked it, so sorry about that. But each of these additional exercises is from here. All right. Now you can, now all the solutions are revealed, so you can just open them up, see what the solutions are. I would again recommend, please, try to work on these and figure them out before you look at the solution. Only look at the solution as a guide, just to check yourself. And yeah, and you can do the ones that I don't assign as well, right? Just for extra practice. There's loads of these at the end of every section. All right, not loads, but there's plenty of additional exercises for you to practice at the end of every section. And I would recommend, not only doing the ones I've assigned, but also just for extra work and to get more used to the material, doing ones I didn't assign as well. And if you have any questions on those, let me know too. Okay, and that was it. All right, that's it for section 1.1. You saw all the participation activities. I didn't complete them all. You're going to do that. And you saw that there was only one challenge activity, and again I didn't complete it. You should complete that. And you're not going to see exactly the same problems I saw, right? But the way you do them is the same. And hopefully this was informative. And this is what I'm going to be doing for every single section, just kind of scrolling through, showing you what's going on. Do some, just start you off on some of the participation activities, start you off on the challenge activities, do some pen and paper work. And yeah, so that's it for section 1.1, and thank you very much for watching.